Hello everyone, welcome to the third tutorial for the computer and network security course. So today we'll be discussing modes of blocks. So let's start with our first question. So the figure below shows the encryption diagram for the AES XTS mode of encryption, an encryption mode that we never took before actually. It's just a new one here for the sake of the question, so let's bear with it. Now, this AES XTS mode of encryption, which is used for data storage. So this is an encryption mode used for storing data, or for data storage in general. In the figure below here is a 128 bit value known as the tweak. So here we have I as the tweak that is rarely changed, and J, which is the number of disk sectors to be encrypted, and we have alpha, which is a 128-bit fixed value, and PJ is the data block in the jth sector to be encrypted, and CJ is the resulting ciphertext. So here we know that this I here is a 128-bit value known as the tweak that is rarely changed. So we can assume that it's a constant. And what we have next is the value J here for alpha J. So this is also this is the J is the disk sector number, and alpha is a 128-bit fixed value. So here this J changed for each disk sector, so that PJ is the jth sector to be encrypted, and the resulting cipher is the CJ. So the first question here asks, okay, so let's continue reading the last thing. The system uses two symmetric keys, K1 and K2, for AES blocks. So we have two symmetric keys, K1 and K2, for these blocks. So what do we want to do? We want to determine the formula for the encryption for calculating CJ. So let's try to break this diagram down to make it easier. So I can break it into two things: this sub-block and this sub-block. Why? Because as you can see here, this the sub-block here, let's go with number 1, and this block is number 2. Block number 1 takes no inputs from block number 2. So we can start with it. We can model this block that outputs T, then use it in this block. So how can we do this? We can start with T equals, so T equals what? T equals all this part here XORed with AJ, or alpha J, sorry. So what is this? It's an encryption block. It's E of I. It encrypts I using K2. Then we XOR it with alpha J. Just as simple as that. And we have our T. So let's go to the second sub-block. Now, we want us to go from the PJ up to the CJ, go down to the CJ, which is the cipher. So CJ is equal to PJ here XORed with the output we had from T. So we can say it's PJ XORed with T. And then we encrypt all this using this encryption block with key K1. So we can put an equal here and do an encryption block here with K1, and then finally we XOR this all again here with the same T, and we have our cipher block CJ. So the second part of the same question, it says determine the formula for decryption and draw the decryption algorithm. So what would we want to do here in order to decrypt? So if you want to decrypt, it means that we have the cipher here and we want to reach the plain text. So I will break this down again into two subblocks. So it will be this one and this one. So remember in the last tutorial we said that if we have an input here for an XOR that is XORed using a certain value, and we have our output, if we want to reach back the input in this side from this output, all we need to do is to XOR the output here with the same value that was used when getting it. So basically, if we want to reach the plain text from the ciphertext, we want to XOR the cipher here with T, the same exact T, and then we will have the output from the encryption block here. We decrypt it using the same key, so we have the same value that was here. We XOR it again with T, and we end up with the plain text. So basically we have the same exact T. We don't need to change anything with the first block here, with the first sub block here with T. So T will be equal to, just the same as we did it before, it will be encryption of I with K2 XORed with alpha J. And what we will do here, we want to get the PJ, which is the plain text. So PJ will be equal to CJ XORed with T, and then it goes to a decryption block here. So it will be CJ XORed with T, and this goes to a decryption block with key K1. And then we XOR all this here with the same T. That's it. As you can see, it's actually very simple. So the third question here, if an error occurs in the J block of the ciphertext, CJ, how many blocks will be affected in the decryption? So let's try to understand this question. So this question says that assume that some error happened with the value here. Whatever bug happened, it corrupted, or whatever something happened, it corrupted cipher block value here. It says how many blocks will be affected in the decryption. So as you can see, each block is only based on the plain text here and the keys and some fixed values. So basically, if a cipher block is corrupted for some reason, it will not affect any other blocks, either previous blocks or future ones. So it means that there is no chaining actually here, so errors do not propagate. Now with the second question. Assume that a regular cipher chaining encryption algorithm which processes blocks of 16-bit length. So if the last block is less than 16-bit, it will be padded with zeros on the right. The block cipher encryption consists only of a permutation given with the table below. The key defines how often the permutation is applied on a block. On the other hand, chaining is done using an XOR operation, and it says encrypt the following plain text. So let's try to understand the question here. So here we want to do a regular cipher blockchaining encryption algorithm. So this algorithm processes blocks of fixed length, which is 16-bit length. And if a block contains data that is less than 16 bits, it gets padded with zeros on the right. So we fill the rest of the bits with zeros on the right till we reach 16 bits. Okay? So it says here the block cipher encryption here consists of only a permutation given with the table below. So here, this block cipher encryption uses the permutation table, the one here. So actually the values are not really easy to read. Oh, they are fixed here. Okay. So this is the permutation table. It's not correct in the previous slide. So as you can see, it's these are numbers. These numbers represent the order of the bits in the output. I will show you how this will be used. And then we have the key, K1. It defines how often this permutation needs to be done. On the other hand, the chaining is done using an XOR operation. Okay, so we have two things to do here, and these are good. We do chaining using XOR, and we do permutations using this permutation table. So we have, let's discuss the givens we have here. We have an initialization vector. So since we'll be chaining using XORing, it means that we will be XORing the output of each block with the next one. So since we have only one block in the first time, so we will need something to use it to XOR with the first block. So that's why we usually start with an initialization vector. And we have the permutation table, the one here. As I said, it's the reordering values of the output. I will show you how to be used. And we have the key K1. It means that we will do one permutation only for each block. We have our chain operator, which is the XOR. Finally, it says here convert letters into 8-bit blocks using ASCII conversion. So A is equal to 65, B equal to 66, C is equal to 67, and so on. So you can Google what is the ASCII conversion system. So what we will do, we will go and basically we will go and Google the ASCII values for these letters, or we go and write down. We can go actually and write down the values starting from A, B, C, D, E, F, G, all the way to Z, and we keep incrementing the value starting from 65 up to the latest value for the Z, and it will be also correct. They are sequential. So for simplicity only, I got you here the table for the ASCII decimals and the binary for each of the letters that we will need to use. Okay, so let's start with the first step. As you can see here, the question said that the blocks contain 16 bits, and here our letters, each letter consists of only 8 bits. So basically this means that we will have 2 letters in each block. So for the first block, we will have the R and O. So we have 82 and 79. We convert them to binary. So what will happen here actually is that we will have the R, which is 0, 1, 0, 1, 0, 0, 1, 0, and then the O, we'll concatenate it with the R, which will be 0, 1, 0, 0, 1, 1, 1, 1. Then what we do next is we XOR this with the initialization vector. So this is our O. We XOR this with 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, which is our initialization vector. So 1 and 1, 1 XORed 1 is 0, 1 XORed 0 is 1, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 0 is 0, 0, 1 is 1, 1, 1, 0, 0, 0, 0, 0. So this is what we end up with after XORing the initialization vector and the values RO. Now what we will need to do is to permute. So as you can see, this value is just the one here, which is, wait a minute, okay, so what we'll do next is we permute this value with this permutation table. What does this mean? So the first value here is 10. It means I will go and search for, note that we start here from 1 up to 16. So we do not start from 0. So 10 here, it means I will go and search for the 10th digit here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is this 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, which is this 0. Cross it out. And this one will be here. Then 3, which will be this 0, will be here. And then 5, which is 1, 2, 3, 4, 5, which is this 0, and I will cross it out from here. And then 16, which is the last 0, and I will cross it out and take it here. And then 7, which is 1, 2, 3, 4, 5, 6, 7, which is this one, I will cross it and take it here. And then 2, and then 2, which is this one, I'll cross it and take it here. Then 1, which is this one here. Then 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is this one, I'll cross it, take it here. And then 11, which is this one, cross and take it here. And then 14, 15, 16, which is this one, I'll cross and take it here. And then 8, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, which is this one, I'll cross it and take it here. Then 6, which is this one, take it, cross it and take it here. And then 15, which is this one, I cross it and take it here. And then we have 9, 3, 4, 5, 6, 7, 8, 9, which is this one, cross it, take it here. And then we have 4, cross it, take it here. And then 13, which is this one, cross it and take it here, I guess. So that's it. This value is just the same as this one, as you can see here. 0, 0, 0, 0, 100, 100, 3 ones, 0, 0, 1, 0, 0, 0, 0, 100, 100, 3 ones, 0, 0, 1. So this is how we do a permutation. Now we are done just with our first 2 letters. What we do next, we do exactly the same for the second 2 letters. Let's do it here fast. So, okay, so we get the bit values, binary values for the C and K. So it will be 0, 1, 0, 0, 0, 0, 1, 1, and we concatenate the K with it, which is 0, 1, 0, 0, 1, 0, 1, 1. And then we add, bear with me in this. This is the CK, correct? We do not add the initialization vector this time. We add the old output. Remember the output of the previous block. Remember it was 4 zeros, 100, 100, 111, 001. Remember that? This was the output of the permutation. So we take it down here to be 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1. So let's do our XOR. 1 and 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 0, 1, 0. So that's it. Now what we do next is we use the same permutation table and do the same permutation again. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have here the 10 as the one, since it's the first value here. And then 3, so this one will be here. And then 5, 1, 2, 3, 4, 5, it will be this one, it will be here. And then 16, which is this one, it will be here. And then 7, 1, 2, 3, 4, 5, 6, 7, this one, it will be here. And then 2, this one, it will be here. And then 1, this one, it will be here. Then 12, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is this one, it will be here. Then 11, which is this one, it will be here. Then 14, which is this one, it will be here. Then 8, which is 3, 4, 5, 6, 7, 8, which is this one, it will be here. And then 6, which is 3, 4, 5, which is 6, which is this one, it will be here. Then we have 15, which is this one, it will be here. And then 9, which is this one, it will be here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, correct. So we have 4, which is this 0 here, and finally 13, which is this 0. So this value here is 1 0 1 0 1 1 0 1 1 0 0 0 1 0 0 0. So 1000. Okay. So seems correct, just the same like the one we did in the previous slide. Okay, so now for the next block, again, now we have the next two letters, which is the N and the R. So what we do here, we get the two values, which is 0 1 0 0 1 1 1 0, and then 0 1 0 1 0 0 1 0. And we use the output from the previous block, which is 1 0 1 0 1 1 0 1 1 0 0 0 1 0 0 0. So let's do our XOR, which is 0 1 0 1 0 1 1 1 1 0 0 0 1 1 1. Okay, so what we do now is we do our permutation. So the 10th letter, the 10th digit, 1 2 3 4 5 6 7 8 9 10, which is this one, it will be here. And then the third one, which is here, it will be here. And then the fifth one, which is this one, will be here. Then the 16th one will be here. And then the 7th, which is this one, will be here, and then the second, which is this one, then the first, which is this one, and then the 12th, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is this one. It will be here, and then the 11th, which is this one. It will be here, then the 14th, 14, 15, 14th, which is this one. It will be here, and then the 8th, 2, 3, 4, 5, 6, 7, 8, which is this one. It will be here, and then the 6th, 4, 5, 6, which is this one, will be here, and then the 15th, which is this one, it will be here, then the 9th, which is this one, it will be here, and then the 4th, which is this one, it will be here, and then finally the 13th, which is this one. So it is 1, 100, 4 ones, 0, 0, 1, 0, 1, 1, 0, 1. So seems exactly the same as the permutation here. So it's correct. Now, with the next two letters. So what we did here was the N and R. What we do next is the O and L. So it's this O, it's not a P, it's an O, and this L. So what we do here, as you can see, the value is correct. So it's just a typo here in the alphabet. So what we do here is we take this one, which is 0, 1, 0, 0, 1, 1, 1, 1, concatenate it with 0, 1, 0, 0, 1, 1, 0, 0, and we take the old output, the previous one, which is 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, and we do our XORing. So it will be 1, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1. So we do our permutation. I will just skip to it for this one. It will just be the same like the last ones. So this is our permutation: 100, 100, 10, 10, and the rest zeros. So let's go to the last block. I will do this one just because it has something different. So in this block, in the previous block, we did the O with the L. So in this one, we have only L left. So we have 0, 1, 0, 0, 1, 1, 0, 0. So as we said, the block needs to explicitly have 16 bits. So in this case, we do not have two letters to fill the 16 bits. So what we need to do is to pad with zeros. So we do it like this. We add 8 zeros to the value. And what we do next is that we XOR it with the previous output. So the previous output was 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, and the rest is zeros. So let's do our XOR. 0, 0, 0, 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. Okay, 1, 0, 1, 1, 1, 1, 0, 1, 1. Okay, so far so good. What we do next, we do our hopefully final permutation. So the 10th letter, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10, which is this one, will be here. And then the third, which is this 0, it will be here. And then the fifth, which is this one, it will be here. And then the 16th, which is this one, it will be here. And then the 7th, 3, 4, 5, 6, 7, this one, it will be here. And then the second, which is this one, it will be here. And the first, it will be here. And then the 12th, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, which is this one, it will be here. And then the 11th, which is this one, it will be here. Then the 14th, 14, 15, 14, which is this one, it will be here. Then the 8th, 3, 4, 5, 6, 7, 8, which is this 0, which will be here. And then the 6th, which is this one, it will be here. Then 15, this 0, and then 9, which is this one, then 4, which is this one, and then 13, which is this 0. So, seems correct. Oh, this is it. This is the output of the final permutation, which is the final output of our cipher block. Now, with the third question here. So, third question here says, let block cipher with secret key K be chained in the following way. So here the blockchain goes as follows. The cipher is equal to the message of the previous block, m of I minus 1. M of I means the message of the current block. M of I minus 1 means the message of the previous block, the one before me. It's the plain message or the plain text of the previous block. It gets XORed with the encryption of the current message XORed with the cipher output of the previous block, all with the key K. So it says here that M0 and C0 are fixed public initialization vectors. Remember, we said initialization vectors are fixed values that we use when applying our cipher algorithm to the first block. So K here is a secret key known to both transmitter and receiver, and we have E and D that represent encryption and decryption respectively. Determine the equation for decryption and draw the block diagram. So, I will start with drawing the block diagram to give you an intuition of how this will work. So, the first thing here that we can start with is the following. So we have M0 and C0 as initialization vectors. So technically, our first message should be M1. So let's assume that we have here M1, and we want to get out C1. So the first thing that we will have to do in order to get C1, we have to get this M1 and XOR it with C of I minus 1, which is C0. So we get here, we have here C0, which is C of I minus 1. C0 is the public initialization vector, and we XOR it with the M1. Then this goes down to an encryption block with key K. So we have an encryption block here with key K. And this output here gets XORed again. This output here gets XORed with the message of I minus 1, M1 minus 1, which is M0, which is, in the first case, it makes sense to be the initialization vector, which is M0. Okay, so what we have here as output is CI, which is finally C1. Let's try to draw the second block to give you an intuition about how this works. So I want to encrypt the second message here, which is M2. So what will happen here, M2 should go to the same XOR. We're doing the same algorithm, remember? So M2 here will get XORed with C of I minus 1. So basically, in this case, C of I minus 1, when it's when I is equal to, it will be C1. So basically, I will be XORing with this one. Okay, so what happens next? I will go to the encryption block with key K, and then I go and XOR with M of I minus 1, which is what? Which is this one here, which is M1 in this case, not M0 anymore. And I have my C2. And I keep doing this. So as you can see here, this one is chained. Chained, it means that each block is connected to the one to the previous block and to the next block. Okay. So let's try to write down the equation for the decryption. So what will we do if we want to reach the M1 here from the C1? What do you think? The first thing we will need to do here is to XOR the C1 with the M0. Remember, the same M0 in order to reach the output of the encryption block that was here. So in order to get MI, we have to XOR CI here with M of I minus 1. Okay, that's the first step. And then we decrypt all this here with the same key K. So we need a decryption block here with the key K. So we are able to hop in here. And then we XOR all this with C of I minus 1. And just now we reach our original message MI. Okay, now with the second part here in question 3. Suppose that ciphertext CJ is damaged in the transmission. Which plaintext block will be decrypted incorrectly? What do you think? So basically, the chaining here not only depends on previous message or ciphertext, it depends on both. So basically, if there is an error with the C ciphertext output, it will result in errors, or it will we will not be able to to correctly decrypt all the subsequent blocks. Basically, because we have a faulty output. Let's say we encrypted everything correctly, but while we're decrypting on the other side, one of the blocks, the output of one of the blocks got corrupted. So basically, you will be using a corrupted ciphertext here as input in this XOR every single time. So you will end up with corrupted ciphertext every single block. So basically, it will all be one. Now with the fourth question. So now Alice and Bob agree to communicate privately via email using a scheme based on RC4, but want to avoid using the same secret key for each transmission. Alice and Bob privately agree on a 128-bit key K to encrypt a message M consisting of a string of bits. The following procedure is used. They use the following procedure in the encryption. Choosing a random 80-bit key value V, generate a ciphertext. Ciphertext is using RC4, which is an encryption algorithm. They use RC4 to encrypt V concatenated. This is a concatenation sign, so we stick things together. So V concatenated with K, and then this encryption output is XORed with the original message. And then this gets out our ciphertext C. And then they send the bit string V concatenated with C. Suppose Alice uses this procedure to send the message M to Bob. Describe how Bob can recover the message M from V concatenated with C using K. So now let's think of what Bob would do. What does Bob have now? So Bob is having the key K, which is the key shared between him and Alice, the one she used here to do the RC4. And he has this V concatenated with C, and he knows that the value V is 80 bits. So one thing that he can do, he can use cryptanalysis, and he can just assume that he will take the first 80 bits of the V concatenated with C. He will just take the first 80 bits and use them as the V, and take the rest of the message, and this will be his C. So now he knows how to get his V and C. So now he has V, which is the random secret key, and he has C, which is the ciphertext. Now what's left? Okay, so, and he has already the key K. So now he knows this algorithm. How can we use K, C, and V in order to get the message M? What do you think? Remember when we said that if we XOR something with something else and get an output, if we want to reach this original message from the cipher, we XOR it with this thing. Since he has the V and the K, he can recreate this RC4 encryption, correct? So he has the values. So he can do RC4 of V concatenated with K, and he has the correct values here for the V and K. And here, instead of XORing it with M, he will XOR this with the C. And this will get him, guess what? The original message M. Okay, so if an adversary observes several values, V1 concatenated with C1, V2 concatenated with C2, and so on, transmitted between Alice and Bob, how can he or she determine when the same key has been used to encrypt two different messages? By key here, they mean the key value, V. So basically, an observer can know this if he sees the first 80 bits to be exact in two different messages. So this might not directly help him to decrypt the messages, but it can help him in his cryptanalysis technique. It can make it much easier for him to be able to break the messages later, because it gave him a piece of information that he did not have, which is the size of the key and its position in the message. That's it. Thank you so much. See you next tutorial.